Okay, in the previous video, we learned about the idea of a basic function, or the way that we discussed it was parent terms and basic expressions. And you could take a parent term or a basic expression and turn that into a basic function or basic relation. And I wanted to make that video before we went through section 2.6, transformation of graphs, in this video. Okay, so this section starts by talking about, they want you to recognize basic functions. So if you're not familiar with what a basic function is at all, go check out the previous video, or I'll put a link to it in the description as well. But it's not just a function, it's a function or a relation. Really, with transformations of graphs, really what we're thinking about in this section with transformations is we're applying certain modifications to an equation, and you think about it, an equation can be graphed, and those modifications make predictable changes to the graph, to the basic form of the graph. So the basic form starts out a lot of times at the origin, centered at the origin, but it doesn't, not always, but a lot of times. So it's unshifted about the X or Y axis. It's unstretched or shrunk about the X or Y axis, and it hasn't been flipped, like a mere flip about the X or Y axis. That's the basic form of an equation or a function. Because again, you can graph both a relation that's not a function as well as a function. And as we go through this section, kind of like we did in the previous video, I want to have some tunnel vision for the most part, in that we're going to focus on two dimensions. So graphs in a plane, or equations or functions with two variables. But everything we're going to talk about in this section applies in three dimensions as well. So as we go through this section in this video, I'll branch off every now and then and to explain how everything is extended into multiple dimensions, or more than two dimensions. But for the most part, for the sake of analysis, we're going to just sort of have some tunnel vision in two dimensions. Okay, so before we get started, the main idea is that you have any equation in front of you, whether it be a relation or a function, and we're going to just focus on two variables at the moment. Has to be something that you can graph. So we're never talking about an equation in one variable, but you can graph an equation in two variables, three variables, or more. When you get past three variables, you have to think about graphing it abstractly, because you can't think past three dimensions, but you can still abstractly think about the idea of a graph in past three dimensions, and I'll talk about that as we go. I'll expand on what I'm talking about later in the video there. But again, so just thinking in two dimensions, for the sake of analysis, you would look at an equation or a function with two variables, and then imagine that it has a graph, or you could be also looking at its graph, and you want to kind of be able to see through the graph in the sense that you break down that graph, you decompose it in terms of all of the different transformations that have been applied to it, the shifts, the shrinking or stretching, the flips. You can see through that equation and see what the basic function or equation is, underlying that a general equation or function that you would see. Okay, so as we go through this section and look at all the different transformations, to give examples, I'm going to use parent terms, like one of these parent terms. So we're just going to transform a graph like this, like f of x is equal to x, or f of x is equal to x squared, or x cubed. Square root of x, just a parent term. But then I'm also going to do some examples with a more complex function in relation that are some combination of parent terms. That's what you would see in general. We talked about this idea in the previous video. In general, you'll see functions and relations that are combinations of parent terms, not just a single parent term, which is what I call a basic expression. So we'll do examples with the function x squared minus the absolute value of x cubed plus x to the 5/2. And then we'll do examples with the relation x cubed plus y cubed is equal to 6xy. Okay, first we're going to start with vertical and horizontal shifts or translations. Okay, so the book gives an example that they do examples with. Here they're going to do an example with this parent term here, just x squared. F of x is equal to x squared. Okay, but again, we're also going to be doing examples with this function here. And so what the idea is, when we do these examples, you can think about extending the concepts here to any arbitrary function that has any kind of combination of parent terms, and then this relation here. So here is the graph of this function. So this is the basic expression, because there's been absolutely no transformations applied to any of these variables here, into any of these terms. And you'll see what exactly these transformations are as we go through this video. And then here is this relation here. It's not a function, right? It doesn't pass the vertical line test. But same idea. There's been no transformations applied here as well. Okay, so a vertical and horizontal shift. They give an example here. So f of x is equal to x squared. And what they do is they just add a constant to the back end of the function. If they add a 2, it shifts the graph up. It's like a rigid body shift. Like the graph does not change shape at all. It just literally just moves up or down. If they add a 2, it shifts up 2 units. If they subtract a 4, it shifts down 2 units. Okay, these are called shifts or translations. Okay, so vertical translations of graphs. Consider a function defined by y is equal to f of x. Let k represent a positive real number. If you have y is equal to f of x plus k, you just add it onto the back end of the function. Then that shifts the basic function with no modifications applied, k units upward. If it's f of x minus k, because k is a positive real number, if you subtract that onto the back end of y is equal to f of x, then it shifts the function k units downward. All right, they give examples here. If you have the basic function g of x is equal to absolute value of x, and you subtract 3 from the back end, you can see it takes the function absolute value of x and shifts it down 3 units. The shape doesn't change, it's just a pure shift. Here they have the function, the basic function x cubed with a 2 added to the end of it. If we come here, it shifts the graph of x cubed up 2 units. Okay, so that's our first transformation, a vertical shift. You could take a basic function or relation that has a graph and shift that graph vertically, up or down. Just a pure shift. It's like rigid body. The shape of the graph doesn't change at all, just a shift. But this is a little bit confusing because when we look here at these more complicated function and relation, so it makes sense here. What we just learned makes sense here. You just, to the back end, plus or minus 3, let's say. This will shift it up or down 3 units, depending if I choose a plus or a minus. So let's do that. Let's do plus 3. Here is the basic function without the plus 3. And here's that same function with the plus 3 added. It just shifted it up 3 units. It looks like it's been stretched, but that's just because I zoomed out a little bit to get this whole graph in. It's a pure vertical shift. The shape hasn't changed at all. The shape hasn't changed at all from this. All right, but how does that apply here? Do I just do this? No. So this is how you have to think about it. Remember we talked about how to make a function, one way you can look at it is if you have any kind of expression of just x, no matter how complicated it is, the vast majority of the time, unless, we talked about this in the previous video, unless it has like a plus or minus in it, like the quadratic equation, or it's some unique function that specifies that for every input there's going to be multiple outputs, the vast majority of the time, in general, any expression of just x, no matter how complicated it is, you could just set that equal to y, and that's a function. And you can replace that y with the f of x. The reason is because, remember, when you might think, well, what about when we have an even root then? But if you're just given an expression that has an even root in it, but that's a principal root. You just return the positive root. You're not solving the equation and adding the root yourself. So just an expression, there's never a time when, if you're just given an expression as it is, there's never a time where you get 2 values out of that unless it's like the quadratic equation and it has like a plus or minus in it. Okay? So with that in mind, we can think about this. Let's every time you have a function, if you're thinking about it in terms of transformations, replace that f of x with a y. Okay? What we're going to see is when we get to horizontal translations, to translate the graph horizontally, we're going to add or subtract a constant from the x. So if we let's come back to this x squared. So let g of x is equal to x squared plus 2. This was x squared shifted vertically by 2 units, vertically upward 2 units. If we want to shift this to the right horizontally, we're going to see that we would do x, and to the right it would be minus 2 squared. So if we wanted to shift this vertically shifted graph, it's already been vertically shifted, and now we want to shift that to the right, let's say 3 units, just to change it up. 3 units, we would subtract 3 from x. Now, you might be confused. Why are we subtracting? I thought we were shifting it to the right. It's the opposite. If you're going to shift it in the positive direction, you subtract 3 from x. Okay, with that in mind, if we come back to this function here, if we want to shift the graph along the y-axis, it's really the exact same concept as what we're going to learn for how to shift along the x-axis, what I just previewed. You come to the y term and you say, so I want to shift this 3 units upward in the y direction. I would say take that y value and do y minus 3. So let me do this. Now it's been shifted upward 3 units in the y direction. But for a function, you always just have y is equal to the expression of x. So they just, what you can look at this like is, let me just add that 3 to the x expression. It's always the same thing. You're just going to be adding it with a function. You're just going to be adding it to the back end. You see? Okay, but what about this relation here? Well, the idea is it's the exact same concept as we're about to learn for how to shift along the horizontal axis. You apply that for the vertical axis by subtracting the amount you want to shift in the vertical direction upward to the y. So if we want to shift this relation, if we want to shift this vertically upward by 3 units, I would subtract 3 from y. It's the opposite. If you want to shift upward, you subtract. That's because we did subtract here. It's just whenever you add it to both sides, it makes it seem like it follows the same direction pattern. If you add it to this end, it shifts it upward. But really, we're subtracting it from y. So to shift this upward, I would do this. And I would do it to each y term in the entire relation. You do it to every y term. Okay, let's take a look at this graph. There you go. It's the same exact graph, just shifted upward 3 units, right? We go from here to here. This is this relation. Okay, translating a graph horizontally, I just previewed how this works, but you just subtract from every single x term, you just subtract the value you want to shift, add or subtract the amount you want to shift to every single x term in the function or relation. If you want to shift it in the positive x direction, you subtract the amount you want to shift it from every single x term. If you want to shift it to the negative x direction, you add. Okay, so if I want to shift, we're coming back to the basic. We've come back to the basic function. We haven't shifted in the vertical direction for either one of these. If I want to shift both this and this to the left, let's say the negative x direction. Well, okay, let's come to the simple example first. So here they start with g of x is equal to x squared. Okay, here's x squared, and they want to shift it to the left 3 units. They just add 3 to the x plus 3 squared, and it shifts it to the left, you see? And then just to point out, if they also wanted to shift it, they want to shift it to the left 3 units and shift it up 2 units, they would just add 2 to the back end of this. So x plus 3 squared plus 2. That's been shifted horizontally and vertically. Okay, so that's the idea for a parent term, just a single term. That's the simplest case. But for the more complicated examples, if I wanted to shift this to the left 2 units, I would add 2 to every single x term. So y is equal to x plus 2 squared minus the absolute value of x plus 2 cubed plus x plus 2 to the 5/2. Let's take a look at that graph. Okay, so we start here. Here's the basic function. That's this here. And now this function, there you go. Shift it to the left. And the same idea, if I also added 3 here, it would just shift this up, this exact graph up 3 units as well. And I'll do an example of that here. Let's shift this relation to the left 1 unit and down 4 units. So to the left, we'll do x plus 1 cubed plus, and then down 4 units. So y plus 4 cubed is equal to 6 times x plus 1, y plus 4. Okay. Okay. Here is the basic relation. No modifications applied to any of the variables. Okay. And then here's this relation here. It's been shifted to the left 1 unit, down 4 units. Okay. Now a couple of things to point out here. When it comes to functions or relations with combinations of parent terms like these, you might also see something like y is equal to x minus 2 squared minus absolute value of x cubed plus x plus 4 to the 5 halves. Okay, so what does this mean? Well, with something like this, you're just going to have to think abstractly. We started off with how we talked about in the previous video. You would describe this basic function here as a combination of a cubic parent term, and that's subtracted from a quadratic parent term subtracted from a cubic parent term contained within an absolute value, and that's added to x to a fractional exponent that's greater than 0. That's positive, let's say. That's the underlying basic function. And then when you look at the transformed version, you can't say that this is just pure transformations applied as a whole to the entire basic function. You'll have to say this is a quadratic basic function that's been shifted to the left 2 units, subtracted from an untransformed cubic parent term contained within an absolute value, added to a positive fractional exponent parent term that's been shifted to the left 4 units. So this is shifted to the right, this is shifted to the left 4 units. That's that's the best you can do. I don't know how you actually make sense of that in your head, but that's the best you can do. And then if you had, plus 3 added to the back end, then you could say everything I just described as a unit is shifted up vertically. This entire graph here. Okay. Now, what about more than 2 variables? I mentioned I wanted to touch on equations that, had more than 2 variables potentially. Well, okay, you can't think about a graph if it's an equation of 1 variable. You can't think about that graphically at all because there's no relation there. You're not relating in any kind of input to output. But any equation with more than 2 variables, you could think about it graphically. And even when you get past 3 dimensions, you could think about it graphically. You could think about it abstractly from a graphical standpoint. But let's look at a 3-dimensional equation. So you have a function or a relation that has 3 variables in it. X, Y, Z. Okay, so you give an XY pair, that gives a point in this plane. And for every point in that plane, once you put an XY into the equation, you could solve for Z, right? Z, at that point in the plane, you go up or down in the Z direction. So you can plot, you get 3D surfaces. You'll learn about 3D graphs in Calculus 3. When you start Calculus 3, you'll do like algebra. You look at algebra in 3D right when you start Calculus 3. But you can think about the same idea. You could have a function or a relation in 3D with the vertical line test. If the vertical line passes through the graph at 1 point, then it's a function for any vertical line. If it passes through 2 or more points, it's a relation. But okay, so if you have an equation that's a function or a relation with 3 variables, it's the same idea. If you can think about shifting that graph along the X, Y, or Z direction with the exact same procedure that we discussed here. You just add or subtract a constant to each one of those variables if you want to do a pure shift of the entire graph in an X, Y, or Z direction. And let's say you have more than 3 variables, 5 variables, 6 variables, whatever. Well, there's no way to graphically think about that anymore. We can't graphically think about anything outside of 3 dimensions. But you just have to think about it abstractly. You can still think about that same idea abstractly. So if you have X, Y, Z, L, W. Well, I can't draw a fourth dimension here, but let's just imagine these are extra dimensions. Well, it's the same idea. You can just abstractly think about shifting along the L direction or the W direction. Same idea. Okay, now there's more than that. There's also the idea of, you'll learn that you can have equations that have one or more inputs. Like all I've talked about so far is an equation with one or more inputs, 1, 2, 3, 4, 5 inputs, and one output. X, Y, and then the one output Z. X, Y, W, L, and then the output Z. But you're going to learn about equations as you progress in math and engineering and et cetera. You're going to learn that there are equations that you could have one or more inputs and one or more outputs, like a vector valued function, for example. Or you can think about linear algebra. I mean, that's just talking about linear equations, but this idea applies to even nonlinear equations. You could have multiple inputs, one or more inputs, and corresponding to one or more outputs. So I could have input X, Y, Z, and that maps to WL. And this could be a function. You might say, well, how is this a function? There's two outputs. You have to think about this in the sense of, like, okay, we used the slot machine example, let's say. Okay, if you land on something, that's an input, and then what you win a trip and some money. Each time you win, you're going to win a trip and some money, depending on what you landed on. $500 in a trip to the beach. If you land on something else, you'll win $1,000 in a trip to New York. That's still a function, right? Because it's not, the idea of what makes something not a function is if you can't land on something on the slot machine, and then it maps to $500 in a trip to the beach, and then you land on that same thing again, and it also maps to $1,000 in a trip to New York. Because then, which prize does it give you? Does it give you both prizes? It's kind of broken, right? And that's what vector valued functions, vector fields. Each point maps to a vector. Well, a vector requires a magnitude and direction. It's two-dimensional. All right, but so if you have an equation like something with X, Y, Z with 3 inputs and 2 outputs, it's the same idea. If you have to abstractly think about, you could shift the quote-unquote graph. You can't really imagine a graph anymore, but along the X, Y, or Z directions. And you could shift it along the W or L directions. What do I mean by that? Well, we could shift in the output direction, right? We were shifting in the Y direction. That's like the output. We could shift in the Z direction, same method. Well, we could shift in the W or L directions with the same method. Okay, so that's translating a graph horizontally or vertically. All right, now another thing we can do is we can apply vertical and horizontal shrinking and stretching. And this would be about the X or Y axes. You could do a horizontal stretch or shrink about the Y axis, or you could do a horizontal stretch or shrink about the X axis. Okay, now what we did with translating the graph, those were rigid transformations. The stretching and shrinking are non-rigid transformations. So the graph is gonna change shape. It's not just going to translate. And they give an example here that you start off with f of x is equal to the absolute value of x, which is this here in gray. If they multiply, this is all about the coefficient. If they put 2 in front of the absolute value of x, they get this. If they put 1/2, they get this. Now, okay, what I want to do is, the way they present it, I find confusing. This is what they're saying. It's similar to the vertical and horizontal translations. This is what they're saying here. Okay, when we get to the horizontal stretching and shrinking about the x-axis, what they're going to say is, if we come here, they say that if you want to stretch if you want to shrink the graph about the x-axis, shrink, not stretch, shrink, you put a multiplier, a coefficient times the amount you want to shrink it. So if you have f of x, and then you make it f of a times x, then the graph is shrunk by a factor of 1 over a. And then if you want to stretch it about the x-axis, you multiply each x by 1 over the amount you want to stretch it. So here a is less than 1. So like, okay, well, first of all, what do they mean by stretch or shrink? What exactly does that mean? Here's what it means. If you start off with a basic form of a graph, f of x, if you are shrinking that graph by a factor a whole number factor a, just think about a positive number at the moment. We're not multiplying any variable by a negative number. Let's think about any positive number that's greater than 1, okay? If you are going to shrink that graph f of x about the x-axis by a factor of a, you're taking every single point on that graph and dividing the x-coordinate by a. So let's say you wanted to shrink the graph by a factor of 2. What would you do? You would have f of x, and you would change it to f of ax. You wouldn't multiply. It's the opposite, kind of like it was for the translations. It's the opposite. You don't say f of 1 over a times x. You say f of ax, and that takes every point and divides the x-coordinate by a. If you want to stretch the graph, which means by a factor of 2, let's say, then that means you would have every x-coordinate would be multiplied by 2 and the y-coordinates unchanged. If you did nothing to the y variables, then you do f of 1 over a times x. You see? Now, I wanted to talk about the stretching and shrinking about the horizontal axis because really you can think about it as far as vertical stretching and shrinking. It's the exact same concept as the horizontal. Because what they show here, they say multiply, they have a function here, and they say you multiply it by 2 to stretch it. All you're doing there, if I wanted to stretch this graph about the y-axis by a factor of 2, by the y-axis, I just use the exact same principles as they outlined for the horizontal stretching or shrinking. I do this, 1/2 y. See, if you come here, I would do 1/2 times f of x. You multiply both sides by 2, and that's where you get this, 2 times the absolute value of x. I'm stretching it. Here, I'm shrinking it about the y-axis because I would multiply the y times 2. Okay, so let's try this out. Let's stretch this graph here by a factor of 2 about the y-axis. So here's this function here. I zoomed out a little bit so we can see the stretch. But this is a basic function here. It's this. There's been no transformations applied. Okay, so to stretch this graph by a factor of 2 about the y-axis, we multiply by the reciprocal of that factor, 1 over 2. That's what you do. You multiply each variable by the reciprocal of that factor. So if I wanted to stretch it by a factor of 1/2, that's not stretching it, that's shrinking it, right? Because it's less than 1, between 0 and 1, I would multiply by the reciprocal. I'd multiply this by 2. But for the case of a function, you can see with a function, it's easy to see how this works because with a function, you've just got f of x or y is equal to the full expression of x. If you multiply the whole equation by 2, you're multiplying the entire expression by 2. Which again, what does this mean? If we're going to stretch this function about the y-axis by a factor of 2, that means we're not changing the x variable and we're multiplying each y value by 2. That's what it means. Each y coordinate. So this y coordinate, it's right below 2. So this position is going to stay it's going to stay the same position. It's going to come up to about here. The x value is not going to change. It's going to double. It's going to come up to about here. The entire graph is going to do that. There you go. You see? It's been stretched vertically, right? So if we come back here, we start with this basic function. If we do a vertical stretch by a factor of 2, each point, you can take the y value of each point, multiply by 2, and don't change the x. If you're going to shrink it by a factor of 2 about the y-axis, take each point, don't mess with the x, divide the y by 2. That's what you're doing, okay? If we come here, a horizontal shrink, same exact idea. You multiply by the reciprocal of the factor you're wanting to shrink or stretch by, each variable, each x variable by that. And so we start with, here's f of x. And they want to plot f of 2x and f of 1/2 x. So this is f of 2x is going to shrink this about the x-axis by a factor of 2. Each point, the x value of each point is divided by 2. The y value is unchanged. Right? This point, divide the x value by 2. Minus 4 to minus 2, it comes in. Here, it starts x is equal to 2, y is equal to minus 2, but the y doesn't change. It's just x is divided by 2. Here, x is equal to minus 2, x is divided by 2, now x is equal to minus 1. And the stretch is the exact same way. That would be this here, it would stretch it. So, okay, if I want to do a horizontal shrink, let's say, by a factor of 2 on this relation, on this here, well, just do this. Each x, it's a shrink, so multiply each x by 2. Just like that. And it'd be the same idea here. So let's take a look. There you go. Each point, the y value hasn't changed, but the x value has been divided by 2. It's been shrunk about the x-axis. All right, but same idea as translations. I could shrink about the x-axis and at the same time stretch about the y-axis. Like you could do both. I could apply a shrink and a shrink about the y-axis, a stretch about the x-axis, and also a horizontal or vertical shift. And at the end of this video, we'll talk about there's an order you want to do transformations in so you don't screw up your graph. But you can apply all types of transformations. And it's also a similar idea in that, you know, this maybe only this is stretched. So maybe I've got y is equal to 2x squared minus the absolute value of x plus 3 cubed plus x to the 5/2. Well, now it's going to be, the way you decompose this is, all right, the basic function is this. A quadratic subtracted from a cubic contained with an absolute value added to a positive fractional exponent. But the function I'm looking at, the quadratic has been stretched, or no, it would be shrunk by a factor of 2 about the x-axis, and that's subtracted from a cubic that's been shifted to the left by 3, contained with an absolute value, and that's added to an untransformed positive fractional exponent, right? That's the only way you could describe it. And then when you look at this graph, it's going to be harder to see the transformations visually, explicitly visually, like we could see if we did it to every single transformation to the entire function as a whole. Like we could see the entire vertical shift, the entire horizontal shift. We could see actually explicitly see the stretching because it's taking place to the whole graph as a unit. So let's look at that. Let's look at, okay, we've got this. Here's the basic function, right? But now we're not going to apply a transformation to the whole graph as a unit. We're going to be applying certain transformations to the components of this basic expression. So you're not going to be able to see it. Watch. Let's take a look. Okay, well, the graph actually isn't even recognizable anymore. Let's take a closer look and see why. I think this would be a good exercise. So we went from this graph, which is here, and then we applied these transformations, and now we're here. We just shrunk this parent term by a factor of 2 about the x-axis. We shifted this parent expression or term here to the left by 3 units, and we left this unchanged. And that made the graph go from this to unrecognizable. You can see I'm zoomed out a good bit. Here we're zoomed in. This is between minus 4 and 6. Here this is really zoomed out. So this is the graph. So what happened? Okay, here is the green is x squared, the purple is absolute value of x cubed, and the black is x to the 5/2. Because the black is undefined for x is less than 0, this sum here is undefined for x is less than 0 as well. So let's just look to the positive x-axis. You're taking the green value and then subtracting from that the purple value and then adding to that the black value. So at x is equal to 2, for example, 2.5 about right here, you can see you're going to take the green value, subtract the purple, and then add the black. But as you get bigger, as you get further along the x, the purple really starts to take over. See here, we can't even see where like we got this green value, but then the purple's way up there. Now the black is trying to pull everything back up. The black's trying to keep up with the purple, but eventually the purple overtakes everything and this goes to negative infinity. The purple is much larger than the green and the black's trying to pull it up, but eventually as you get higher, the purple really overtakes the black as well. Okay, now let's apply these transformations. Okay, here is the x squared has been shrunk about the horizontal axis. So this is a little more zoomed out, but this green is going to be shrunken in. Every single x value is going to be divided by 2. This is more zoomed in than what I was just showing. Okay, the purple is shifted to the left 3 units, and this is the black's unchanged. Well, yeah, you can see what happened. This entire graph was just yanked downward by a huge amount because look, for like x is 1, you got the green minus the purple. Well, the purple is going to, by the time the purple finally gets to x is equal to 1, it's an enormous value. And then the help coming from x to the 5/2 is just this, because you're adding these two and then subtracting the purple. Let's do x minus 1. Let's shift the x to the right. Let's shift the purple just to the right. That'll be a little more recognizable of a graph. We're going to get for any point, like for this point, we'll get, you add the green and the black and then subtract out the purple. Yeah, we're going to get it should be more recognizable as far as comparing to this, the initial basic function. Okay, here it is. I had to zoom out a good bit as well. You could see it pushed this lump up. Before it just pulled that lump out. It just pulled that lump was gone. It just yanked the whole thing down. Just yanked it all down. Now this is going to 100. This just goes from 0 to like 6. This goes from 0 to 100. So, but you get the idea. The point is, you get the idea of decomposing these graphs, and it's going to be complicated if you've got mixtures. If you haven't performed transformations to all of the x variables as a unit, or even in this case, all of the y variables as a unit, then it's going to be harder to see the actual transformations, but you can still think about the idea of how it's built up. Even if it's something like this, where it's just every single parent term, you have a combination of parent terms and every single parent term has been transformed differently. You can still decompose it and see the parent function behind it and see how it's been transformed in general. Okay, the last type of transformation is a reflection across the x or y axis. All right, if we come here to here's just the general summary of this. All you're going to do is, and I don't like how they present this for functions. Here's what you do. If all you want to do is apply reflection, then to every single y variable, if you want to apply reflection about it would be it's like the opposite. So, okay, if you want to apply a reflection about the x-axis, then put a minus sign in front of every y variable. And I say every y variable, but if you're talking about a function, then it's just going to do that. If you're talking about a relation, you would do that. And this would reflect the entire graph about the x-axis. I know it's confusing. It's like everything's the opposite. Why does it reflect about the x-axis? Because what you're doing is each of these graphs has a point x, y. Okay? Just as they are here, without any transformations. If you do this, what does that mean? That's what you're doing if you're reflecting about the x-axis. Think about this. So if we come here, here's f of x is equal to x squared. So y is equal to x squared, you could say. You say minus y is equal to x squared. Every y value, this has a y value, you're mirroring that over here. You're saying this is y, now I'm going to make it minus y. It's reflecting about the x-axis. Okay, here you've got f of x equal to the square root of x. They want to reflect that about the y-axis. They put a minus sign in front of the x. G of x is equal to the square root of minus x. It does this. That does this. Reflects it about the y-axis, you see? All right, let's do that for the complicated function in relation. Here's the function. Let's reflect this about let's do the y-axis. So I would put a minus sign in front of every x value. Okay, let's see what this looks like. There you go, reflected about the y-axis. Okay, let's reflect this about the x-axis. So you put a minus sign in front of every y value, which is, you're doing the same thing for a function, but it's simple. You just do that. Then I've reflected it about the x-axis. Here I do, okay, let's see what that looks like. There you go, reflected about the x-axis. I put the minus sign in front of all the y's, it's reflected about the x-axis, and then same ideas as we talked about, you could reflect about the x and y-axis, and you could, think about the idea of only, this is a combination of parent terms to create a basic expression, but maybe only some of those parent terms are flipped and others aren't. Same idea. Okay, there's one last thing we need to talk about. As I've mentioned, yes, you could start with any basic expression, and you could apply any combination of transformations you want. You could do a vertical shift and a horizontal shift. You could stretch. You could combine all of those different types of transformations together. That's fine. However, if you have some transformation in mind that you're going to apply, or you're mentally trying to decompose an equation or a function, see the transformations and the basic expression behind it, you need to do it in a certain order. If you don't do it in a certain order, it's not going to work like you're expecting it to. Okay, if we take a look here, you want to, if you have starting with a basic function and you want to modify that equation to a basic function or relation, you want to modify that equation to have some overall transformations, you want to do it in this order from 1 to 4. You want to do the horizontal shifts first, then the horizontal and vertical stretches and shrinks, then reflections across the x and y axis, then the vertical shifts. You want to do it in this order. And if you're going in the opposite direction, if you're trying to decompose a function or a relation, mentally decompose it, you want to go in the opposite order. Take away the vertical translations first, then take away the reflections across the x and y axis, then take away the horizontal and vertical stretches and shrinks, then take away the horizontal translations. Why do you want to use this order here? Well, it's nothing crazy. It's just more of, you technically don't have to use that order. But if you don't use that order, you're very susceptible to screwing it up. As long as if you understand the transformations well enough about how they're being applied to the equations, you could go in any order you want and just be careful as you do it. But if you don't go in that order, it's very easy to mess it up. So take a look at this example. It says transformations involving a horizontal shrink, stretch, or reflection. Horizontal. So applying a minus sign to the y to reflect it, or applying a factor to the x variables, often introduce confusion when coupled with a horizontal shift. To further illustrate the rationale for the order of the steps, begin with here's a function, y is equal to the square root of x. Performing a horizontal shift first means we replace x by x plus 2. Okay, so we've shifted it horizontally to the left by 2 units. The parent function y is equal to square root of x. Then to perform the reflection across the y-axis, we replace x by minus x to get the y is equal to square root of minus x plus 2. So we want to apply the reflection, right? So we put a minus sign in front of all the x values to shift across the y-axis. To reflect, okay? Now, what if we performed those in the reverse order? This worked. What we just did here worked. We shifted and reflected. We shifted it 2 units and then reflected it. But if we do this in the reverse order, what happens? Okay, you first reflect, so about the x-axis, and then you replace x by x plus 2, and you get this. The square root of minus x minus 2, you see? What you wanted was this, and you instead got this. You see? So just keep that in mind. And also the last thing, there's another thing I want to point out. If you have, so let's come here where we have some extra space. So if you have a graph and you apply, you imagine you apply a shift in the x direction and y direction. So let's say this graph here is shifted down and to the left. So now it's here. That's like x cubed. So you applied the horizontal and vertical shifts. Now, if you want to apply a vertical or horizontal stretch or reflection, you're not doing it, you're not stretching it about these axes, you're stretching it about imaginary x and y axis that are at where the origin was shifted. You see, you get what I'm saying? If you shifted it here, let me see if that's the right order. You do the horizontal shift, then you do the stretching and the shrinking and the reflections, then you do the vertical shift. So, okay, let's do this. Let's take this x cubed and do some transformation. So we shift it, let's say to the left first. Okay, now you want to do your reflections and your shrinking and stretching. If you do a vertical stretch, you're not stretching it about this axis. You're stretching it about an imaginary y-axis that's at where the new origin is. If you do a reflection about the y-axis or x-axis, you're reflecting it about this imaginary axis at where the new origin is. Okay? Okay, so let's work some example problems.